Good evening, ladies and gentlemen. It's my pleasure to welcome you all to the public lecture titled Learning Through the Failure, How Aviation Incident Influenced the Policy and Regulations. Today we are telecasting this webinar online also. Online we have another 13 to 14 members join. So physically also we have around 20 participants. So thank you for coming here today for this webinar. So we are truly honored to have with us a speaker, exceptional global stand-in expertise, Engineer Bimal Aponsu. Engineer Bimal Aponsu currently serves as the Chief Scientist and Technical Advisor for the Dynamic Systems at the Federal Aviation Administration of the United States. With over 35 years of professional experience, his career spans the most critical areas of aviation engineering, including flight dynamics, aircraft handling qualities, vehicle stability and control safety systems, and advanced simulation development. Before joining the FAA, Engineer Aponso served as a NASA Ames Research Center, where he was the chief of the Aeronautics Project Office. In this role, he provided technical leadership for several landmark initiatives, including the X-59 low-beam flight demonstrator, a project that is redefining the future supersonic flights. His work has also contributed significantly to the next generation AI-space technologies and safety critical system demonstrations. Earlier in his career, he spent more than 2 decades in the industry, developing advanced flight control and simulation systems, bringing theory with real-world aviation applications. His academic background includes degree in mechanical and aerospace engineering, complemented by an MBA, reflecting both technical and in-depth strategic leadership. Today's lecture will be with us rare and valued perspective on how aviation accident and incidents are simultaneously analyzed, and how the lessons learned translate into the regulatory reforms and improve the standards and safer sky worldwide. This is a topic of immense relevance, not only the aviation engineers, I think all of us safer skies for the safer skies in the worldwide. And today's lecture is very valuable for all of us, as I mentioned earlier, not only as an aviation engineer. I am a mechanical engineer. So as doing a building services field, engaging. So I also interested to participate this lecture to learn beyond our knowledge, general knowledge, to enhance the general knowledge. So I think Engineer Bimal Aponso can deliver a lot of vast experience with us, share his experience with us that is beneficial for all of us, I think. So without waiting much time, I will invite Engineer Bimal Aponso to start his presentation. Engineer Bimal Aponso, it's all to you. Yes.
Thank you, Mohan, for that introduction. Truly an honor for me to be here. I left Sri Lanka when I was 18, I think. And so it's great to be able to come and share some of my experience with all the engineers here. And I've been lucky enough to be able to indulge my passion. So I'm happy to share those experiences. Before I get started, several people I should thank. I want to thank Kosala Kamburadeniya. He's the president of the IESL. Mohan Vijayasinghe, who just introduced me, and Neil Abhisekara, the CEO of the IESL. Thank you for the invitation. It's truly an honor. A couple of other people I want to thank somewhat. My relative, Xavi Fernando, who persuaded me to spend my vacation preparing slides. And Pial Naka, who disseminated information on this to both my St. Thomas's Colupitia classmates as well as my Royal College classmates. I told him I have no place to hide if I go wrong. And most importantly, my wife Devika, who's sitting back there, who encouraged me to overcome my usual reticence to give public speaking, to kind of give this speech. She shared her valuable vacation time and let me just prepare slides. So, and also, she made it possible for me to indulge my passion by running the family and bringing up our son. So thanks. With that, let me sort of talk about, and as Mohan said, I'm going to try and it's about aviation, but I think there are lessons that can be learned throughout engineering and even the business fields. And I'm sure a lot of business people know. One of the basic rules of life, I think, is the risk-return ratio, right? The more you risk, the more potential upside, but the more big potential downside as well. But then living a risk-free life also is not, you don't progress, right? So, and that's why the old adage goes, nothing ventured, nothing gained. And sort of related to that is, you risk something and you fail. But they also say failure is the best teacher. As long as you, and something my wife and I always told our son, failure is okay. You just have to learn from it and, improve. And it really is the best teacher. It's so much so that in Silicon Valley now, which I've spent 15 years, one of the questions they ask at interviews is, well, how many times have you failed? They want to see that you've tried new things and learned from your failures. So how do you do that in an aviation concept? In an aviation construct, failure can mean, human life, right? It's a matter of life and death. So how do you balance that? How do you make the industry grow and innovate while really kind of, making sure it's safe, right? And the hinge point there is learning from the failures. So every accident is a tremendous opportunity, unfortunate as it is, tremendous opportunity to learn, change regulations if you have to, change industry standards, and then make sure that or similar accidents don't occur again. That's what the system is built on. So with that sort of background, another one thing, I have about 20 slides. It's probably I'll talk for maybe 40 minutes, but I'll mostly enjoy is questions from all of you at the end. So I look forward to that. Tee up all your questions and I'll do my best to give you my 2 cents worth on everything. The other thing is I'm pretty impatient with PowerPoint, so my slides are pretty basic. And one other big thing is I'm not here representing anybody except myself. So with that said, let's go on. Okay, let's try to. Okay, good. So maybe I will stay here, right? I came up with, me and a colleague of mine, kind of what we try to do is we try to, what are kind of few questions that the audience might be interested in? So these are the kind of questions I'm going to try and answer in that. How important is in this particular aviation to the economy? And what's the purpose of regulation? Why regulate at all? Let industry self-regulate. Why do you want to do that? Are regulations the same for everyone who wants to operate an aircraft? Do you apply the same regulations to an airliner as to what guy who wants to fly during the weekends? Why do you what's the interaction between regulation and innovation? I kind of just alluded to that a little bit before. And then how incidents used to improve. That's kind of one of the focuses of the talk. And what have we learned from past accidents goes together with that. And what have we learned? Has it made a difference in current aviation? So to the first question, let's see if I can pay this. Oops. What you'll see here is what you call the day in the life of the US airspace system. What you'll see is it's starting at like midnight, and you'll see the aviation system begin to wake up, and you'll initially see the middle of the country. You'll see somewhere around there, Memphis, where the late night package carriers, FedEx and so on, start their operation. You see Memphis here as a big spot of activity. All the flights are sorted out and they start sending the packages out. Then as daylight begins in the East Coast, you see the East Coast beginning to wake up, right? And what you'll see is just a sheer volume of aircraft. These are all managed by the FAA, right? And you can see some Atlantic flights going this way, a few Pacific flights coming into the West Coast. But now as the daylight goes westward, you see the flights across country and the other cities start to wake up, right? And you can see the big hub. You can see Atlanta somewhere down here. You can get Chicago up here. But you can see this area as the New York airspace, one of the most crowded airspaces in the world. But all this happens safely, right? It's an incredible feat of just combination of regulation and evolution of regulation and practice and the following of the regulation. So you see all the flights beginning to now stream off to Europe at that time, right? All the cross-Atlantic flights. So, and here you see the flight count. I think I can't remember if it started at about, okay. So, and let's stop there, I think. There's more that goes on. You can find this on YouTube. The next segment shows what happens when there's weather and everybody. And this is an interesting fact. The US airspace system to handle that, every 2 hours, it used to be a teleconference. It's now a webinar between all the control centers. The airspace is built into en route control centers, terminal control centers, and airports. Every 2 hours, there's a teleconference on our webinar where they talk about issues at various places and they plan the airspace. And so it's a really interesting operation. Next slide. Thank you. So, by the numbers, here's the US airspace system. Fiscal year 24, it runs from October to October, but it's really, year 2024. 16 million plus flights annually being controlled by the FAA. 44,360 flights daily. You can read all this. But at peak load, typically there's like 5,500 flights being managed by the FAA airspace system at any given moment at peak load. Another thing that a lot of people don't realize, there's 28.6 general aviation hours here. One of the largest users of the airspace is general aviation, not the flag carriers, not your United Airlines. It's the doctor who's flying recreationally, is the business jet person who's flying his important passengers. There are little, now we have things like net jets where you can actually, hire a piece of a jet and, so a lot of recreational flyers, everything from people flying a Cessna 172 to flying their own kit-built aircraft, right? So that's a democratization of that airspace. Anybody should have access to the airspace. And that's one of the challenges of keeping it safe. It's worth 9.8 million jobs. $502 billion, and it represents about 4% of GDP. This is not only the aircraft manufacturers, the airlines, the services, the airport, the taxi guys that run, all that depends on one thing, and that is the public's confidence that they can go from point A to point B safely. That's the one thing. And I think when I met with the DGC office last night, I emphasized to them too, that you are the front line in Sri Lanka, right? You have to ensure that Sri Lanka is safe to get in and out of. That is a really important job. And it all hinges on the public's perception of safety. If there's a slight drop in that, your economy is going to suffer. Right? So that's the mantra that we, at least the FAA, that's the way we look at it. Right? So how do you do that with the, what's the regulatory framework? The way it's done in the US, at least, the FAA administrator is by law, Congress told it's an executive office of the FAA, created, in this case, under the Department of Transportation. And that of the FAA administrator's job is to maintain a minimum standard of aviation safety. You set the floor here. Everybody, all the industry, all supposed to be above that floor, right? That's by law, that's what the overall broad policy for the FAA. How does the FAA do this? FAA has the authority to regulate and also to enforce regulation. If somebody does not meet the regulations, you can enforce actions, you can fine. FAA also has been given the authority by Congress, which is by the people, to do that. How does the FAA do that? There's a series of regulations called the Federal Aviation Regulations. And these are some of them. Aircraft law Part 91 covers general operating rules. If you're flying in the airspace, you need to have a transponder. You need to have basic instrumentation, so essentially like saying, if you want to drive on the road, your car needs to have rear view mirror, and it has a lot of sort of rules on basic rules. Then on top of that, you have commercial airline operations, which are Part 135, which are, if you're going to run an airline, you're going to charge passengers, then you need to have, certain equipment, you have to have maintenance standards, all those regulations that come under, that make sure that's safe. Again, minimum standards of safety. Then pilot certification, medical covers that. And then the aircraft design, you get Part 23, 25, 33. 25 is the large transports, the Boeings and the Airbuses and so on. And Part 33 is engines. I'm pointing these out because I'm going to talk about them a little later when I talk about the incidents. And then you get maintenance. And basically, and in the aircraft certification, which the area I work in, aircraft certification and policy for certification, essentially what you have three certifications for an aircraft. There's a type certification, there's a manufacturing certification, and an airworthiness certification. So type certification, the manufacturer has to provide evidence that the design of the aircraft meets all the regulations. A manufacturing certification certifies that you can now manufacture this aircraft exactly according to the design. And the airworthiness certification says that the whole comes out the way you designed it, that the aircraft flies, it's airworthy, all that. So there's those three kind of legged stool on which aircraft are certified. And and it also hinges on the regulations. Essentially what they say is minimum standards. So because the FAA is not in the business of designing aircraft, what the FAA does is sets basic standards, says, if you have an engine in Part 33, if fan blade cracks and flies off, you have to be able to contain that within that engine. It must not fly out of the engine and damage the fuselage or anything. So there are some basically, but they allow the manufacturer to design it as they want. So typically what they do is the regulations, the manufacturer shows evidence that they comply with the regulation. The FAA looks at it, and what they do is define compliance. It's not a legally, it's not an approval. It says, yes, we believe what you say, and that's enough, right? But ultimately, it's a manufacturer that's legally liable if anything goes wrong. And if the manufacturer falsifies information or does something, then the FAA can come back and find them. There's lots of regulatory, what they call the stick approach to deal with that. So, okay, so now trying to deal with the democratization of the airspace. So when you regulate, you want to have, in the US at least, everybody be able to access the airspace because it's a public right? So you need the person with a Cessna flying on the weekends, to a private jet, to an airliner, all need to have access to the airspace, but you can't apply the same regulation to all of them. It's not fair. It's too burdensome. And so Congress again set up a thing, said that that when you're prescribing regulations, you have to consider the duty of a aircraft carrier to provide a service with the highest possible degree of safety, but also consider differences between air transportation, commercial air transportation, and other types of air commerce, right? So if you try to apply the same rules broadly, then it will become too burdensome and will not allow access to airspace for the helicopter flying medical, equipment, emergency stuff, the private pilot flying for pressure. So and these rules kind of from that basic tenet is, and the way the FAA looks at it is what's called the safety continuum. So you have up this way, you have the various types of operators. So right down here, you'll have the people flying drones up to, people who build their own kit aircraft and fly them. There's a lot of them. To, small airplanes, seaplanes, all the way up to commercial airline. And then on this axis, you have the perception of the public demand for safety in the airspace, right? And you'll notice that what is assumed here is the public demand for safety increases as you get up to the larger and larger commercial transportation. Particularly as you get up to here, now you're charging the public for a service. They expect that service to be rendered safely. Can you get two? There is a line here. You notice this line is sort of asymptotic. There's a line here where it's 100% safe, zero accidents. Well, what's that? You don't have an aviation suit. You don't fly, right? That's the safest thing to do. So what you try to do is to make it as safe as possible without really killing the space. So it's a real delicate balance. And so, when you apply the safety continuum, again, sort of to expand on that, the way the FAA looks at it, there's risk and there's a safety effort. If you don't apply enough safety, then you have accidents because there's a lot of escapes of, you just miss stuff. If you apply too much regulation, then you're so involved and it's very prescriptive, there's no innovation. There's no safety improvements. People are not allowed to innovate. So what you try to do is to hit this, the FAA is always trying to try to hit this middle area where you allow innovation, but also allow, also ensure safety. Now, that means you're going to have accidents and you're going to miss some. And that's where the whole issue of learning through accidents becomes really critical to this whole paradigm of managing safety as well as allowing innovation. So just a quick word about some of the regulations, just to show where the public perception is really important. And you'll see later on some of the accidents, changes came because the public really advocated for them. Initially back in the 1930s, nothing really sort of galvanizes the public opinion rather than famous people. So in 31 and 4 years later, a couple of crashes killed some really beloved, well-known people. Well, they established a civil aeronautics act and said, okay, with the safety board, started ensuring if we want this airline system to be relevant and successful, the industry, then we need to set a level of safety. We need to regulate. Didn't do that until the public came up and said, okay, you need to regulate. And then there were two media collisions, one over the Grand Canyon, one this was en route over the Grand Canyon, flying visual. This was in the terminal area in New York. These two accidents had made sort of resulted in large changes in the air traffic control system. For example, after this, they basically said all aircraft are going to be under radar control. Previously, the airplanes got on a airway route, and the airplanes were allowed to visually separate and go on. And what happened in this crash is one guy deviated to sort of look at the canyon, get a better view for his passengers from both sides. The other guy, they didn't quite hear the call, and they hit each other from an angle that they didn't see, and the wreckage you can still see at the bottom of the canyon. They never got it out. Anybody who's interested in aircraft, that's one of the most beautiful aircraft ever built, the Lockheed Super Constellation. And then there are these four accidents. I just noted them because I'm going to be talking about them, and I'll talk about what those spurred on. So, and here's a statement we make all the time. Just about every rule out there is written in blood and iron. So which means accidents are what have really caused the system to be, change and improve. Learn through failure. Always learn through failure. Not that you want failures to happen, but that's an inevitable part of trying to allow innovation and people to progress. So key in this is the United States Congress set up the National Transportation Safety Board in 1967. This is a very important part. A very critical part of this is it's a completely separately funded agency. They are not part of the Department of Transportation. They are essentially, you can almost call it a law unto themselves. So they are not reliant on funding from anybody else. So they are then free to provide completely unbiased opinions on accidents. And they actually talk about any kind of transportation accident. Most famously, you hear about them in aviation accidents, but big bus accidents, or even pipeline issues, anything that's used to transport stuff, they will look at it. If you notice, I think even the oil well blow up in the Gulf of Mexico, they investigated. So it's a very critical part. Now, it's funded separately, and the FAA must, when they make recommendations, FAA must consider does not act on all of them, but the FAA has to say, yes, we agree with this, and here's what we're going to do, or no, this is not practical. Yeah. So this is always the relationship in the FAA and NTSB is, not entirely friendly, because the FAA always, from the FAA point, they grumble because, okay, the NTSB has no skin in the game, so they can just say whatever they want. But, they'll say, okay, build new engines and put, well, practically you can't do that. The airlines will go, hey, we are all going to go under, So, but that's the way it works. And so then there is a, give and take. But it is, even annoying as it is, kind of like a free press. It's a very critical part, and everybody in the FAA recognizes that. So on to the accidents. I included some of these, particularly for the pilots out here. This is interesting accident. Lockheed TriStar. Air Lanka flew one of these for many years. Beautiful aircraft. Eastern Flight 401 was a brand new aircraft. It had less than 1,000 hours on it. And what happened was they were coming to land at Miami, and this is, old. I took it off a report in 1972. They were coming in for a landing. They were on final approach. And when you put the landing gear down, you have to see 3 green lights to say that the nose gear and the 2 main gears are down and low. Well, the nose gear light wouldn't go green. So they called the controller and said, hey, we have a little bit of a problem here. Can we climb to 2,000, whatever, until we figure it out and go on. So controller said, yeah, sure enough. And so they climbed up and started, trying to figure out the problem. What happened then, they had actually, and this aircraft had 3 crew, had a captain, a first officer, and a flight engineer, right? They all started messing with the light, right? They all got in there. They pulled the light. They were not sure if the bulb was problem. So they pulled the cover of the bulb out and were messing with the bulb. First of all, they put it on autopilot to hold 2,500 feet. And they were all now captain, and then the captain sent the first officer down into the avionics bay because there's a little flag that shows if the landing gear was down. The first officer came back and said, well, it's too dark down there, I can't see. And so they were all fiddling around with this. While they were fiddling around with this, the captain bumped the control column, which then disengaged the autopilot. And the aircraft started descending. Nobody noticed. When it deviated 250 feet from the altitude that was set, there was a little bing chang that went. Nobody noticed. And somewhere around here, the first officer goes, hey, what's happening? Because they started getting low altitude calls. What's happening? We are 2,500 feet, right? And the captain goes, that completely lost situational awareness, right? And they crashed into the Florida Everglades. 99 people died, 77 non-injured. Perfectly good flying aircraft. The landing gear was down. It was just bad management in the cockpit. So out of that came, it was not only that, but there were several other accidents where these type of cockpit issues came up, where they instituted crew resource management. That had been researched for a while by NASA, and it is now a standard practice for training pilots. They talk about how do you manage one person monitors the aircraft at all times, but the other person does, tries to figure something out. Just the allocation of tasks, but making sure that somebody is monitoring the flight instruments and making sure the airplane's where it is supposed to be. There also were other sort of changes, like making sure the enunciations of changes in altitude will be more compelling. And the other things that came out of it was, this thing crashed on a moonless night in the Florida swamp. It was pitch dark. So even the survivors had no idea, but there were alligators too. And so out of that came, you need to have emergency lighting systems so that when it crashes, you'll have batteries, that there'll be some lighting for passengers to be the surviving passengers. And they also, at that point, the rear-facing crew didn't have shoulder harnesses, and they analyzed it and said, you need to put in shoulder harnesses. Now all the crew, regardless of which way they're sitting, they have shoulder harnesses. So an example of when they analyzed the accident, they didn't only look at what caused the accident, they looked at all the aftermath. Every accident is a chance to learn and improve. So a lot of, as you can see, a lot of the improvements that came out of this had to do with emergency of crashworthiness as well as pilot training. CRM is now a standard thing, and I think Shiv knows all about CRM as the stuff. Another big seminal accident was the the DC-10 crashed in Sioux City, Iowa. So this was, again, old, charts, but the DC-10 was a 3-engine airplane, had one airplane in the tail, one engine in the tail and 2 on the wings. And what happened, so they were flying, here's the start of the track, this is the ground track. They were, climbing out, or they were, I think, in cruise, when the main fan disc of this engine completely fractured and separated. And it was a big piece of the engine. I'll show it in the X-ray. And what it did was, it spewed shrapnel, piece landed and everything on both the tail, horizontal tail surfaces that were each side. And in each of those horizontal tails were the 3 redundant hydraulic lines that were going to drive them. So what it did was, it severed all 3 hydraulic systems line and bled all those 3 hydraulic systems. So right about here, they had a complete engine failure, and then they realized they had no flight control. They could move the steering wheel, the joist, the control column had no effect on the controls. They had no control. And also they had, I think one of the ailerons on one side was floating up because in the fail state, and the airplane kind of always wanted to turn right. What was going for them is that they had taken off from Denver. They had 2 experienced crew members and a flight engineer. That's also had a flight engineer. And they had sitting in first class a DC-10 check captain who was what they call deadheading on that flight. He was going somewhere else. So soon as this happened, he offered to assist. Captain said, come on forward. What they did after that was, the captain was in front, and this check captain knelt on the floor with the control column and manipulated the 2 remaining engines to actually go around. And you can see the aircraft sort of going around in circles, making right turns. And they got vectors immediately to Sioux City, Iowa, which was the closest airport. And they made it to the airport. They actually made it to the airport. But at the last stages, they were off, and the wing dropped and the nose dropped. So it cartwheeled into the cornfields on the side. But it was a remarkable piece of flying. And there were 185 survivors, 111 fatalities. It was just incredible how they brought that airplane back. All 5 pilots survived. The cockpit broke off. And so what happened? So the probable cause was, again, what they said, the probable cause was the failure to detect a fatigue crack. Here's the disc. They found all the pieces of it and they put it back. You can see the crack. It just broke right across here. And all these fan blades, which are typically rotating at around 5,000 revolutions per minute, just flew in all directions. What they found was, they traced a metallurgical defect to the titanium ingot that was used to fabricate this part. It had a little void in the ingot. So, and when they started, making the bows and stuff to build it, they kind of made it worse. And there was a little crack developing, and none of the crack detection methods detected it. So what came of this? They said, okay, we need to do more research on non-destructive testing. Really improve the fatigue crack propagation, understanding all the basic understanding how cracks propagate. And the other thing is the fan casing. This fan casing was supposed to really contain the damage, but it didn't. So, okay, look at how those engine events should be done. And it's interesting. The next event I'll talk about shows the success of whatever they implemented from here. And then they did a lot of research on, okay, if you lose all flight control, how do you control an airplane using only the thrust? And then another, again, they require passenger restraint during landing, takeoff. And I guess there was not a real requirement at the time. They made it mandatory and a requirement for restraints on lap babies. Until I just doing research for this talk, I looked at it. There were 4 lap babies. They didn't have constraint. So what they asked them to do was to put the baby on the floor, and when they're bracing and hold the baby on the floor. One flew up and was caught by the parents. One sort of disappeared, but somebody else found her and brought her out. Of the 4 babies, only one died of asphyxia. So obviously the baby survived, but was breathed in the smoke and died of smoke inhalation. So they, at that point, now require, if you have a lap baby, restrain with the lap strap. So that's kind of what they learned from that. The next accident is Southwest 1380. I actually know about this because I was asked to comment on this as soon as I provide an opinion on this as soon as I joined, even though it had nothing to do with my area of expertise. But Southwest 1380, what happened? Here's the engine. This, here's the engine and the cowling that goes with it. And if you notice, the engine has, if you notice maintenance, there's a cowling, it opens, it latches underneath and it opens for people to access the engine during turnarounds and stuff they can check the oil levels and so on. What happened with this is one of the fan blades broke and flew up. It actually broke at a point where maximum impact was where this latching mechanism, this fan cowl latching mechanism was right under where it actually hit. Now, and what that did is it sent a shock wave and opened the latch. The latch then, the cowling opened in flight. The cowling, one part of the cowling, this side stayed put, this side broke off, flew up and hit the window just about the point where the window flew out and sucked up the passenger who was sitting in that seat out. So that was the one fatality in that incident. So when I looked at this, they had done everything right. None of the fan blade components left the engine compartment. It was all, so if you look at the Part 33 engine certification requirements, it met all that. There is the airframe certification, which is Part 25. There's a requirement that the airframe, the engine attachment to the airframe and its structure should be robust to engine fan blade dumps. And usually what they talk about is when the engine seizes up like that, it stops suddenly, creates a large force on the attachment mechanism. That was mainly meant to solve that, or to prevent that, the engine from breaking off and falling off. But the other thing I should mention is to show that engine fan blade, when it breaks, will stay within the casing. FAA requires the engine manufacturers to do a test to break a fan blade. So they'll take a perfectly working $5 to $6 to $8 million engine, and they will, because the FAA mandates it, blow a fan blade, and there are specifications on roughly where you should blow this fan blade at a 12 o'clock position or something. But somehow all the analysis, and they use that then to improve their structural models to figure out what happens. And what the report basically said that yes, but the modeling was not quite there. And what the report then recommended, even though it worked perfectly and maintained it, it didn't prevent pieces from flying forward. This cowling part fell off. And all of this was looked at really closely because there was a fatality. But the plane came back and landed safely. Again, crew resource management. The pilot was a former Navy pilot. She just managed everything really well. And did some things, made decisions on the fly to do certain checklists, not do certain checklists. And it was really interesting. It was an interesting accident to see, read about, to see how they dealt with that and land safely. But out of that, the probable cause of the low cycle fatigue crack and the fan blade. And at a location that was critical to the structural integrity. So it came apart. It was a series of very low probability events. The fan blade came apart just right where it hit the cowling. The cowling opened up and hit the window just about where the window failed. And when I looked at this and had to remember, this is such a low probability event, but yet that doesn't matter. A person died. What can we do to improve the system? So really, the regulations are being sort of adjusted. There is, there's a gap in understanding, so they're working on improving. And you try not to mess with regulation too much, because right now, quite honestly, it takes about 10 years to change a regulation, because there are so many requirements. You have to go through, public, industry impact statements. You have to go to public comment. You have to disposition all the public committees. So it's better to just get the industry together and say, what are you guys going to do about this? And have the industry sort of self-regulate. Essentially, that's what the FAA did. They convened an industry FAA committee, and they talked about how to improve the modeling that and prevent this accident in the future. The NTSB recommended, Boeing acknowledged that they need to go and redesign those cowling latches. And they have now, in the process of, the FAA has accepted their redesign. They are retrofitting all the older, these are the 77 new generation, next generations. They're retrofitting that at their cost to the fleet. Regulation guidance, and then they also talked about incorporate accidents learned in crew training, cabin crew, because what happened was when they had the person, they had to pull them out of the window, they had to lay them out on 3 seats. Well, the flight was full. So where are the 3 people who were sitting in those seats going to sit? Because they were sitting on the floor during landing. So there was, okay, that's not good. We need to plan for this kind of conditions. What are we going to do? So again, every part of the accident must be evaluated for information that can make the system safe. The last accident. This will be really interesting to the pilots, but here's the Colgan accident. And there's a video that was made by the FAA. So this is a commuter aircraft, Continental at the time. It's Colgan Air. It was flying for Continental Airlines. It was a twin turboprop de Havilland, Canada aircraft. The crew had gone from Buffalo to Philadelphia, Philadelphia to Newark, Newark back to Philadelphia, back to Newark, and this was their last leg for the day. Now they were within their duty day, but they were tired, and it was a little icy, not too bad, and what was happening, you don't see it. They were discussing a lot of different things in the cockpit. They were talking about unions, they were talking about race, they were complaining about. So as you see later, the integrity of the, what they call the cockpit was not maintained. So what you'll see here is how quickly something can go bad, from flying normal to bad. Things to watch for, here's obviously the aircraft. This is what the pilot sees display. You probably can't see that very clearly, but look at this now. This is the airspeed, this is the altitude. Just watch that airspeed. These two are the stick shaker and the stick pusher. I'll talk about that in a minute. This is the power setting, and this is the flap setting. Typically, what they were coming to land at Buffalo. There was some icing, not a lot. The company requirements said they need to slow to a certain speed on approach. They also made two mistakes. And again, there's a good combination of accidents are never of one. It's like a series of issues, errors. And this is getting a little bit technical, but I say it because it's important and I'm sure Kamal will appreciate this. They, like in an airplane, they set a reference speed for approach, right? And in this case, the airplane didn't have a computer on its own, so they call their dispatcher on the ground, they give all the information, and said, here's the weight of the aircraft, give us the reference speed for this configuration. And they came back and they got back a speed of 125 knots or something like that to do the approach. And but what they left out of that discussion was that they were anticipating any icing, right? So they got a reference speed, not expecting any icing. What they did in the cockpit was there is a switch which sets icing. And when you set that switch, it changes the reference speed in the system at which you get a stall warning to a higher speed. So you get a higher speed. So now the stall, the aircraft thinks that it's stalled at 135 knots when they are trying to fly the approach at 125 knots. They missed that. They just didn't sort of understand it, or they weren't paying enough attention. They missed that. So you see what happens here. I'm not going to try and stop this too many times lest I mess it up. But watch carefully the speed. And you see everything's going on right. And you see the person, really reduce the power rating down as he's trying to get the speed down to approach. And at some point, this speed will go red, which is the stall speed as set by the system. The aircraft doesn't really stall. But what happens when you get that stall is you get a stall warning. And as all pilots know, you can't ignore that warning. It just shakes the control column. It shakes it, right? And you get started. And if you don't do anything about the stall in this particular aircraft, because it's susceptible to deep stalls, the control column will automatically push forward to push the nose down, get the aircraft flying. Also, I should add stall. What's stall? Stall is when, if you're flying next time you're flying over the wing, look at as the aircraft gathers speed, you'll see the wing kind of starting to lift up, particularly in the big, 787s and newer aircraft, they'll curve up. And when the airplane, the pilot rotates the nose, you really see the wings bend upwards. That's the airflow over the wings. When you change the angle, it starts providing lift. If you make that angle too much, that airflow breaks down and suddenly you go to no lift. And if you're at a high angle of attack, which wing loses lift first, it's random. And whatever wing loses lift first, will roll in that direction. And working with the control column has no effect because the wings are not producing any lift. The controls are not effective. So you see what happens here. I'm going to just let it run. So they're coming along and his speeds are at 180 knots and he's beginning to get it down. He's getting some radar vectors from Buffalo Airport and they make a turn. And so the power is kind of low. This condition is the RPM, the propeller RPM. And you notice the speed kind of, it's stabilized at about 170 knots. Everything, and they're talking in the cockpit and, going along. They're not really observing. And okay, here's flaps 5. So hot mic 1, hot mic 2, those are the two, captain and first officer. Okay, so they set flaps 5. And then so they get the instruction from ATC and they're still, 180 knots, doing well. Just look at this little red bar here. That's the stall speed. That's a stall speed based on what was set in the aircraft, right? And that's not what they're expecting, because they had forgotten that switch, or didn't know what they're doing. So you see that the red bar is kind of down here, and 180, that's still doing fine. By the way, this is the control column, left, right, and if it goes down, that means it's pulling back. If it goes up, it means it's pushing forward. And 180 knots, 186 knots, and and everything was going well. And he's got the flaps down. His power is almost at flight idle now. He's just really got the power down, trying to get this. And now the airplane starts slowing down, right? He's got the flaps down. I think he also had the gear down. Yeah, he got the gear is down. Now the aircraft really starts slowing down, because the aircraft is very. And you can see this red bar coming up. Boom, the stall warning comes on. The stick shaker comes on. What does he do? He pulls back on the stick, right? The aircraft was not stalled, but when he pulled back on the stick, he stalled the aircraft. Immediately it goes into gyrations, and he's going, what's going on? What's going on? And you can see the airspeed really dropping. The nose points downwards. The stick pusher comes on, pushing the stick forward. He pulls back against that, right? So, and they crash, right? So you can see how quickly just things went bad. And what kind of, human beings, when they get tired and you get startled, you do stuff that's against your training, right? And so 49 fatal injuries, including one on the ground. So that's the class 1. This is an interesting accident because go to the probable cause. The probable cause was captain's inappropriate response to activation of the stick shaker. So the stick shaker said, you're about to stall, and the last thing he should do is to pull back. He needs to gain speed and get their wings flying again. But his instinct was, ooh, I'm close to the ground, pull back. And the aerodynamic stall from the aircraft did not recover. There were lots of other factors, like the reference speeds and so on that I talked about. But this was the main factor. What was important about this was the passengers, relatives, and interested parties formed a very powerful lobby group. And they went after Congress. You need to do something about how pilots are trained for stall. You need to do something about crew fatigue and rest. They lobbied for years, and they got Congress then put into the FAA's. Every 3 years, FAA gets reauthorized, and the Congress puts a laundry list of things that FAAs would do. So thou shalt change the training requirement and the stall training for stall. Previously, the training for stall was it's pretty benign, minimum altitude loss. Here they said, you need to get more serious than that and train. And then you need to also, so these are the contributing factors: failure to monitor airspeed, failure to adhere cockpit procedures, captain's failure to effectively manage the flight, not be a leader, Colgania's inadequate procedure for airspeed selection. That all has to do with the stuff I talked about in terms of the reference speed settings. But the impact was quite large of this accident, and shows the power of what people can do when you form a lobby group. They require the regulations to be changed for the operators in terms of training. Develop and conduct training that incorporates stalls that are fully developed, no longer the small stalls that you can just easily recover from. Fully developed stalls are unexpected, involve sudden autopilot disengagement, and include airspace specific features. So, in fact, the FAA, I was at NASA at the time, the FAA used our simulator to try and train, to look at what you need in terms of simulation capability to do this kind of training. And I mean, I was, my friend was doing that, and so I got a chance to fly some of those. And what they literally did was they had the research pilot would fly, the test pilot would be with a hood. And essentially, they would turn the plane upside down, point it to the ground, and then tell, okay, lift the hood and recover the aircraft, right? And so essentially, you're pointed to the ground, you have to roll the wings level and slowly pull back on the thing without overstressing the airplane. And, in a simulator, obviously, they know they're not going to die. So but then they actually develop lots of simulator procedures to really startle the pilots. And so they would have pilots doing what you call the river approach into the national airport, where you follow the river, and they'd suddenly hit them with a big wind that would cause the airplane to stall and force them to recover. And my friend said, here's video of pilots at that time saying, push, 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 but they're pulling the stick back to their lap. That's how much ingrained that when you're low altitude, that's instinctive reaction. So that's why, so as a result of that, one of my colleagues now actually, and a friend or another colleague, they actually have for the last 7 or 8 years have been going around the world educating different airlines on what they found out, how do you set up a terminator. And it's important. The FAA doesn't get involved in training. FAA advisors, and so hopefully in March, he'll be coming here to give, that Kamal has arranged for him to come and give the training or the education to the Sri Lankan airline pilots. The ATSP said, the simulation models only went up to regular flight. The models were not correct so that, okay, you need to improve your simulation model so that the aircraft behaves as you would expect post-stall. So subsequently, there were several other loss of control incidents. You may have, one of the most famous was the Air France 447 flying at altitude, which was a high altitude stall. And really, that was incredible. For 8 minutes, they fell out of the sky in a perfectly flyable airplane, did not know their altitude, and all 200 and something people died. Perfectly flying aircraft. All they had to do was to push the nose a little forward and gain some speed. But they were so startled. It was a dark night. They had sort of lightning coming off of the aircraft. And so it gets started, and you do things that you don't expect. So this was, how to train pilots to expect that, and to really condition pilots to speed. You need to get speed. So what's the result of all that? Well, I got this over there. Here's the accident rate per million, fatalities per million passengers. And you can see it readily, steadily comes down up to 2021. Now, granted, 2024 was not a great year, but really, passengers really been coming down because a lot of people are flying, and they're flying safely. So they literally say it's safer to fly than to cross the road, right? So that's been the impact. And this hasn't happened, by magic. This has happened because of consistently looking at accidents and improving. Impact on passenger survivability. One of my colleagues was the chief scientist for crashworthiness, and I was talking to him about this stuff. This is, I know you remember, this ASEAN accident happened in San Francisco about the time we were living there. If you see this airplane and if you see the video of this thing, it actually landed short, dropped the wing, it actually cartwheeled and landed there. There was only one fatality, and that was because one passenger got kind of thrown out of the airplane, and I think it's a bit murky, and I think got hit by one of the emergency vehicles. No fatalities. There was like 300 plus people on this airplane. This one, you might have seen recently, the JAL 350, brand new A350 that landed on top of a Japanese Coast Guard airplane that had taxied onto the runway in error. It landed, it caught fire. Everybody survived in this. Why? Because none of the slides exploded in the heat. Why? Regulations. I didn't realize it, you don't see it in that, but my colleague told me right in front of the wing root here on the A350s, there is a light that comes on and shines a light in the darkness to show whether it's safe. And he told me what a lot of discussion and argument there were. And in his description, it was thumping your shoe on the table kind of argument, where manufacturer goes, what? You're asking us to cut a hole in the fuselage and put a light? Yeah. So if you want to be certified, you need to do that. And well, it becomes useful in things like this because they could tell which slide to use and which slide not to use. But it's amazing. Everybody survived. So it's not only the fault of security, but the learning on crashworthiness has really improved and made everything a lot safer. That's it. That's my last slide. And that is the NASA X-59. They mentioned the low boom flight demonstrator. I started being on the review board for that when at its initial design stage. And it flew for the first time. Whenever you work on an airplane, the first flight is kind of a religious experience because until then, it's a bunch of equations. And so this was, I should add, in the US, there are 3 organizations that can certify airplanes to fly in the airspace. One is the FAA, the other is the military, they can certify their own airplanes, and the other is NASA. They can do their own certification, they all test the aircraft, but they all have to have processors the same as the FAA do. So they had kind of a type certification. And so from the very inception, I was part of what they call an independent safety board that essentially cleared the aircraft all the way through design, through first flight. And as soon as the plane flew and landed safely, my job was over. So I had 2 positions at NASA and the FAA, and I'm no longer, although I still have their computer. Anyway, so that's it hasn't flown. It flew. First flight was while we were all furloughed and told to stay at home. But the NASA guys kept working without pay and got it fly. And I think they're all collecting data to before they go on the next flight. So shall we ask me to speak a little about supersonics? So I added that slide. So thank you for attention. Thank you for listening to me. I hope you find something that you can take away, and let me have whatever questions you may have. And I think the next slide shows all kind of some of the different aircraft I worked on in my past. And one special person, a friend, who was Bo Bobko, who was the 3-time shuttle pilot. My wife and I knew him pretty well. He actually worked for me at NASA. Just a gentleman, and boy was he interesting to talk to. He was just fascinating. Whenever I had a chance, I just go into his office and have a chat. And he passed away year before last. So, a real gentleman. So anyway, that's it. Questions?
Did you go from NASA to FAA?
At NASA, I'm an airplane guy. NASA, as I started off running their flight simulation facilities. And the reason I got to know the astronauts and several of them is that NASA Ames, where I work, had the largest flight simulator in the world. It's an 11-story tall building. It's the most capable. That's why the FAA used it to do upset prevention training. They wanted to see, because that had the best motion cues. So all the shuttle pilots trained there for landing. So I met a lot of them. But then subsequently, I moved on to planning projects for them. And a lot of the work that was done at NASA Ames were air traffic management related. How do we make the airspace more efficient? It was great fun. I got to know a lot about the industry and how the airlines, and I got to plan a project which now has been implemented. But, there's just so much air traffic management, more of an operational research kind of thing. I want to get back to the airplane, and my colleague who did the upset prevention, he had been at NASA. He went to the FAA and he goes, "Hey, Bimal, the dynamic systems job is coming available." So I get, "Hey, I don't have a PhD." I'm like, no, apply. So, and I got the job, and so primarily because I like working with my Jeff, who's my colleague. So, and it was a chance for me to also move into policy and regulation, which is something I wanted to, before I ended my career. So this is definitely my last job. It was a hell of a move. I was, past 60 at that stage. I got my wife to uproot from 15 years and move from San Jose, Mountain View to Seattle. But we abide by the mantra that change is good. It's not easy. So anyway, it got me back into the airplane and got me into an area that I really didn't know much about. And boy, have I learned, because in the FAA, in NASA, you plan projects and what you call project goals. The stripes are painted pretty wide. You can deviate, and you can adjust project goals, and there's room. FAA, no. Is it safe or not safe? Are you going to say? And at some point, I keep joking, my friend Jeff, "Hey, I'm an island boy." I kind of go, "Oh, maybe this." Like this. If that plane crashes and Nancy Pelosi is in it, what are you going to tell a congressional informer inquiry? Okay. So yeah, it's I had to really take it seriously and to do. And I'm always amazed that some of the younger engineers who are the front line, who have to deal. And the bigger guys who build airliners, they're fine. There is a huge industry of people who build components for airplanes, and they will go, no, we have this model, we have these very smart people. No, you need to test it and show how good your model is. And they will come back and they will do something else. And these young engineers at the front have to basically sit and say, nope. And then they threaten that they're going to go to their congressman and complain and say, okay, go for it. So it amazes me. And so what might I advise a lot of these people, and with a couple of things I'm going to go back to. I don't know what state it's going to be in when I get back, but yeah, there's a lot of that goes on. It's a huge industry, and the big guys, Boeings and Airbus, they know what they're doing. It's the small guys that buy. It's the small guys who take an airplane and convert it to a water bomber for firefighting, right? There'll be a helicopter. They'll buy surplus military helicopters and want it to carry cargo or medical. They'll make changes to it. Okay, well, they come to us, and so there's a lot of that always going on. It's a vibrant industry. Then on top of that, you get these new aircraft, which are, electric. None of the regulations quite fit. So there's the eternal argument. Now they're talking about autonomous. No pilots. Okay. So what do? Basic rule of flight is to see and avoid. Okay. How can you see and avoid if nobody's on there? All progress, innovation, regulation has to help it along and not stymie it, but yet keep it safe. Sorry, there was another 3. Yep.
That would give them the ground. I'm sure that the problem here could be failure situation or events.
Yeah, yeah.
If any, sports,
Yeah, a good question. In fact, if you talk about CRM, that's another incident where they improved CRM. Cockpit resource management, the Colgate incident talked about no leadership organization. There's another issue of cultural issues. There were several incidents at Korean Airlines, some of this hierarchical, where in that Tenerife accident, the co-pilot, the captain was the chief pilot, I think, for KLM. And he had been sitting on the ground, stuck by fog. He wanted to get home. The co-pilot knew that the Pan Am flight didn't know where they were. Pan Am guys were also listening and saying, hey, we are still on the runway. We don't know where we are. And when this guy captain said, go, let's go, co-pilot goes, I think they're still on the runway. He said, no, they're clear, let's go. So co-pilot didn't assert his authority, and that's why that accident happened. So CRM now, trains that the co-pilot says, no, pull the throttle back, override, right? But it takes a lot to do that. If you're wrong, you're going to be in big trouble. But Korean situation coming into land at Guam, I think, right? Yeah, the Guam accident. You look another. I think if you read the book Outliers, there's a chapter there which they actually Captain Ratwata, Suren Ratwata is quoted in there. He talks about that incident, and that was again the co-pilot knew that they were not in the right place to do that step descent, but didn't say loudly, and kind of got overridden by the captain. The ASEAN accident was also something like that. There were two senior captains. One was checking the other. There was another senior person. The guys were like, hey, somebody should be watching airspeed, and they were not. It was first officer, right? Was it the jump seat, right? Yeah. Yeah. Yeah.
So they say, they need to have exploring all the foreign pilots to come and to manage foreign pilots and foreign pilots for certain duration. They were banned.
Yeah. So
very difficult to announce the stuff. For the first one. So it's taken
So I'll give you an anecdote from what I remember from my father's days as a teenager. So my father was director of civil aviation. I think I won't name any other thing, but one first office, it was the time we were flying the Avro 748s to and from India. One first officer came to our house and told my father that on one flight, the captain who had been his trainee, he's the one who trained him and his mentor, was, put it lightly, inebriated. He had bought a clock, I remember this still, in India, wanted to get rid of the box because to get it through customs. These are the days when, imports are issued. Descended the aircraft, and had the crew open the cargo door and throw the box out. It took like 4 people apparently to pull the cargo door back in, and they bent the handle doing that. People could have fallen out. So he came and told my father. So my father is the direct aviation was everything, right? Was the airports. My father goes, okay, will you testify in an inquiry? No, I can't. Can't do that. So my father had a dilemma. What do I do? He said, okay, there's no option. I have to pull his license and restrict him from flying, knowing that he was going to get overridden because there were connections. And he sure did. He got overridden. So, I think things have hopefully changed. And Sri Lankan has an exemplary safety record, which is good. And I think that's why I told my colleague who's going to come to get the training. I think in Sri Lankan, you'll find pilots are there because they love to fly and they're interested in learning, not because they could become a computer programmer or something like that, right? So I think that's what we have going for us. But we always have to be vigilant that sort of this hierarchical, like you said, the power difference doesn't show itself in the cockpit. Yeah. Yeah. Yeah.
One in when the maybe both answer what is the role of the is it the pilot or
No, it is always the responsibility of the pilot to fly the aircraft, right? So aviators, aviate, navigate, communicate, right? In that order of priority. First thing you keep the wings flying, right? Number 1. 2, you navigate, get to where you want to go, and 3, you communicate what's going on. The role of the autopilot is to make life easy for the pilot, and the airlines like it also because it gives you consistency. So in terms of fuel burn and all that, it gives you consistently, and so airlines will write procedures around it. Autopilots are not part of the certification of an aircraft. You can certify an aircraft with an autopilot. You can fly, manually. The autopilot is what's called an operating rule, right? If you put an avionics system on this with an autopilot, then there are certain set of safety rules that comes under an operating rules that come under Part 91 that says, okay, if you have an autopilot, then you have to essentially deal with the safety. If it knocks off, it must clearly say, hey, I'm off, you're in charge. And there are various other things related to it. It mustn't disconnect with some big transient. So there'll be requirements like that. But in like the incidents with Colgan Air and even Eastern Airlines, the autopilots knock off. And it's a kind of a good point. Autopilots and airplanes have kind of got really much more capable. They've also got more complex. There are lots of modes, and sometimes pilots get lost as to what mode they're in. Or it will disconnect and go into a mode that they don't understand or are not paying attention. Ashiana was They were using the autopilot really to do things that autopilot are not supposed to do on approach. And, they lost control of speed. So the autopilot is there as an aid, but the pilot is always in charge. Yeah. It's always, they keep talking about the max accidents, right? The previous flight before the one crashes, same thing happened. Pilots knocked off the auto trim and flew it manually. It's the same arrangement. Pilot has manual control. The autopilot just drives the control surfaces to keep you at a certain altitude or a certain descent rate. And the autopilot also, there's the autopilot and there's also the auto trim capability that come. But at any point, if the pilot doesn't like what the autopilot is doing, pilot switches it off and flies it manually. In fact, a lot of airlines, it's now, at least in the US, the mantra has come back that pilots should spend a certain amount of time flying manually. So that because what's happening a lot is pilots are getting used to just literally soon after takeoff, you engage the autopilot, and the autopilot is linked to your navigation computer. It's called the flight management system. And your flight is essentially managed all the way up to landing if you want, but typically up to final approach. But what was happening is when something goes wrong, pilots are going, there were a lot of pilots, newer pilots, who were trying to figure out what was wrong with the autopilot rather than figuring out, let's get the plane flying and then figure out what's going. So that has led to, at least the US, encouraging airlines, they can't mandate, but encouraging airlines, and the airlines are interested in safety. So they are using that, letting people fly manually more so that they can keep their skills up. I think they have done some software fixes. I think they put an angle of attack display. And they've alerted the pilots to that, which is one of the things they didn't do before. But the remedy, if something goes, is still the same. You turn off the system. And then you fly pitch and power, which you tend to forget sometimes when you get started. Yeah, I mean, there's an argument that says, the pilot is, sometimes, causing accidents. So the issue with, they're coming, right? Autonomous systems are coming, and there's whole groups of just trying to figure out how to even frame the autonomous aircraft problem. And, literally manufacturers come out and say, and look at the regulations and just want to scratch out everywhere it says pilot. No, you can't do that, right? The issue with completely autonomous systems is you really have to make the system foolproof, right? And the nice thing about having a pilot on board is, the autopilot or whatever autonomous system goes off and says, hey, I can't do this anymore. Here, you're in charge, and relate that back to the pilot, and which is, that's where things happen. But so there's a high standard of safety. Again, where that falls in the safety continuum is going to be a matter of public perception, right? So right now they are trying to, frame it. There won't be a pilot, there'll be a ground pilot. Okay. So if there's a ground pilot monitoring 5 airplanes, do you observe sterile cockpit? Do you do CRM there? How do you, so there's a massive debate going on, research is being done. It's a big conversation between the people, and of course, companies are certified, there are 2 airplanes that are, but none of the electric aircraft companies are certifying them as autonomous. They are certifying them as piloted first. And then the hope is to kind of, as the public and the regulations all kind of come along, to start doing this. And there's no question, we're going to start having accidents. Then we will find out the public's tolerance and then regulate accordingly. So in a way, the regulatory authority has to be, in a way, a step behind, to in terms of regulating, because always the bias is not to over-regulate and overburden the industry with regulation. Any more? Thank you very much. Oh, let's see. The online questions. Oh, my friend. Oh, that's
Triangle complex. That's all, no?
yeah.
Right. Thank you. Thank you. Thank you, Engineer Bimal, for wonderful, inspiring lecture. Before winding up, I would like to have a small token of appreciation. I would like to invite Engineer Savindranath Fernando, Past President IESL, to hand over the token of appreciation. Engineer Savindranath. Right, thank you, Engineer Savindranath Fernando. On behalf of Institute of Engineers Sri Lanka, I extend our sincere thanks to Engineer Bimal Aponsu for delivering an insightful lecture and taking time to come here and deliver, share your knowledge with us, with our engineering community and the aviation community in Sri Lanka. That is vast experience you shared with us. Thank you once again for your coming here and sharing your experience. And finally, I would thank Engineer Shavindranath and the past president IESL for arranging this lecture, taking time and motivating us to conduct this lecture. Thank you, Engineer Shavindranath. And finally, I would like to thank all the participants, physical participants, and online also we had nearly 20 participants. So all the participants, thank you very much for coming here and get vast experience from the Engineer Bimal Aponsu. Thank you very much and have a pleasant evening. Thank you. Thank you.